With the rapid increasing size of wind turbine generators, the transportation and installation of offshore wind farms is becoming a big challenge in the complex logistics around increasing the offshore energy production. Currently, the capacity is around 9 MW per installed turbine, which is expected to increase to 11 MW next year. Furthermore, the latest turbine models being displayed by the major manufacturers will increase further to 15 MW within 5 years. The challenge comes from the sheer size of the components. For example, the blades, though not relatively heavy, are heading towards 130 meters length, which becomes challenging to store on the deck of the ship. When considering transporting the blades transversely on the deck of a ship, the rolling motions could cause the tips of the blades to touch the water. When considering transporting the blades longitudinally, the length of the vessel becomes the limiting factor. Furthermore, the next generation of nacelles are expected to weigh up to 1,000 tons and have to be hoisted to heights of up to 150 meters above sea level. The ships currently used to transport and install WTGs were designed for turbines of about 3 MW, which would weigh around 150 tons and had to be hoisted to 80 meters above sea level. This development has occurred very fast, in less than 5 years, which is a fraction of the lifespan of a typical vessel. To keep up with this progress, vessels have had to go through multiple updates since launch so they can still be utilized in the latest installation of wind farms. How to create giant wind power pillars. It is not located on the mountains or plains, but must be immersed in the sea. Is there any way to resist seawater? Let's learn and discover how to do it on Machinery and Technology channel. Here, at the start of the process, the plates for the cones are pre-cut in final shapes using these smaller shapes. Means make the best possible use of plates, have less cutting loss, and can eventually roll the cone in one single move. Also here, The pre-cut plates for the cones and the plates for the cans will be milled on the shortest sides that are going to be welded together. Here, there are 3 identical assembly lines, where the panels are completely welded from both top and bottom. This means no having to flip the panels to weld the other side. Less handling. Meaning is that this is safer and greatly reduces the handling time for this part of the construction. Once the plates are welded, they will be milled here. After welding, there will be a need to check for welding inaccuracies, which currently means needing a very short feedback loop and being able to instantly adjust your process to prevent these irregularities when repairing panels will be taken offline once the process at this hall is complete, ensuring logistical flow. In this part of the hall, the discs are rolled into the final shape of cans or cones. Thanks to the new process, our cones can now be rolled in just one pass automatically with just one move. From a metal plate, the unique approach of this new technology once again makes the process safer and faster. Since offshore wind turbines are located in oceans and large lakes, the materials used for the turbines have to be modified from the materials used for land-based wind turbines and optimized for corrosion resistance to salt water and the new loading forces experienced by the tower being partially submerged in water. With one of the main reasons for interest in offshore wind power being the higher wind speeds, some of the loading differences will come from higher shearing forces between the top and bottom of the wind turbine due to differences in wind speeds. There should also be considerations for the buffeting loads that will be experienced by the waves around the base of the tower, which converges on the use of steel tubular towers for offshore wind applications. Since offshore wind turbines are constantly exposed to salt and water, the steel used for the monopile and turbine tower must be treated for corrosion resistance, especially at the base of the tower in the splash zone for waves breaking against the tower and in the monopile. 2 techniques that can be used include cathodic protection and the use of coatings to reduce corrosion pitting, which is a common source for hydrogen-induced stress cracking. For cathodic protection, galvanized anodes are attached to the monopile and have enough of a potential difference with the steel to be preferentially corroded over the steel used in the monopile. Some coatings that have been applied to offshore wind turbines include hot dip zinc coatings and 2 to 3 epoxy coatings with a polyurethane top coat. Specialized jackup rigs, wind turbine installation vessels, are used to install foundation and turbine. As of 2019, the next generation of vessels are being built, capable of lifting 3 to 5,000 tons to 160 meters. The large components can be difficult to install, and gyroscopes can improve handling precision. Dynamic positioning has also been used to keep the vibrating pile driver steady when installing foundations. A large number of monopile foundations have been used in recent years for economically constructing fixed-bottom offshore wind farms in shallow water locations. Each uses a single, generally large diameter, foundation structural element to support all the loads of a large above-surface structure. The typical construction process for a wind turbine subsea monopile foundation includes using a pile driver to drive a large hollow steel pile 25 meters deep into the seabed, through a 0.5 meter layer of larger stone and gravel to minimize erosion around the pile. These piles can be 4 meters in diameter with approximately 50 millimeter thick walls. A transition piece, complete with pre-installed features such as boat landing arrangement, cathodic protection, cable ducts for submarine cables, turbine tower flange, etc., is attached to the now deeply driven pile. The sand and water are removed from the center of the pile and replaced with concrete. An additional layer of even larger stone, up to 0.5 meter diameter, is applied to the surface of the seabed for longer-term erosion protection. For the ease of installing the towers and connecting them to the seabed, they are installed in two parts, the portion below the water surface and a portion above the water. The two portions of the tower are joined by a transition piece which is filled with a grouted connection. The grouted connection helps transfer the loads experienced by the turbine tower to the more stable monopile foundation of the turbine. One technique for strengthening the grout used in the connections is to include weld beads known as shear keys along the length of the grout connection to prevent any sliding between the monopile and the tower. Offshore wind turbine components are large. Transporting of components between manufacturing and assembling facilities before the installation is to be minimized. As a result, offshore wind port facilities have been specifically built in the regions with high concentration of offshore wind developments. For large offshore wind farm projects, offshore wind ports become strategic hubs of the supply chain for the installations. Normally, for cable routes with a length of less than 80 kilometers, high-voltage alternative current (HVAC) transmission will be a more economical system because it is a cheaper technology, but is limited by how it can be installed. For longer distances, it must be done by high-voltage direct current power transmission, high-voltage direct current system (HVDC), because of the advantages of reducing power loss and saving energy. Submarine power cables are sometimes installed in harsh environments including high waves, currents, water pressure, or obstacles on the seabed. Therefore, installing submarine cables requires much more complex technologies than installing submarine cables on land. Using high-voltage direct current (HVDC) cables has been a proposed alternative to using HVAC cables. HVDC transmission cables are not affected by the cable charging currents and experience less power loss because HVDC does not transmit reactive power. With less losses, undersea HVDC lines can extend much farther than HVAC. This makes HVDC preferable for siting wind turbines very far offshore. However, HVDC requires power converters in order to connect to the AC grid. Both line commutated converters, LCCs, and voltage source converters, VSCs, have been considered for this. Although LCCs are a much more widespread technology and cheaper, VSCs have many more benefits, including independent active power and reactive power control. In order to transport the energy from offshore wind turbines to onshore energy plants, cabling has to be placed along the ocean floor. The cabling has to be able to transfer large amounts of current efficiently, which requires optimization of the materials used for the cabling, as well as determining cable paths for the use of a minimal amount of cable materials. One way to reduce the cost of the cables used in these applications is to convert the copper conductors to aluminum conductors. However, the suggested replacement brings up an issue of increased cable motion and potential damage since aluminum is less dense than copper. Looking at the video, you can also see that these cables are not cheap. It costs up to $400 per foot, which is not cheap. When you consider the hundreds of thousands of miles of these cables currently crisscrossing the global seafloor, it's not hard to see the massive investment, both private and public. What do you think about this topic? Let me know below in the comments. We really need your contribution to be able to develop better and better.